All right, so we are on the dilations day. So if you are wanting to kind of participate in the warm-up that they have them do, just go ahead and kind of put pause on this video and just think about them. It's not meant to be a super challenging warm-up. We're just trying to have you guys think about the translation rule and just make sure that you're correctly reading it forwards versus reading it backwards. And again, I understand that here it's giving you like blank goes to blank, but it could be as simple as, hey, here's B prime, what's B, and or here's B, what's B prime, and they don't have this visual hint of which way you're going. Make sure that the notation or the word image versus pre-image, that those things let you know which direction you're going. So like I said, if you want to do this, just kind of hit pause, and then I'll just show you the answers here. All right, and let me see if I can just make this go away. Okay, oops, that is not what I was trying to do. All right, here you go. For some reason, this little screen doesn't let me click. There we go. Sorry, yay, videos. So there are the 4 answers there, and again, you get that visual going forward or going backwards, but just practicing reading that. If you have trouble doing this, I don't try to tell people to think like, okay, what mystery number minus 6 is 1? Like that might be easy when it's all positive, but it's like, what mystery number minus 6 is -7? Some people can think through that really easily. The other way to do it is just go in reverse. Like if I'm going backwards, instead of minusing 6, let me add 6. So 1 plus 6 or -7 plus 6. Either way you think about it, it's totally fine. All right, so lesson today is on dilation. So I'll skip past the homework questions. Basically, a dilation is going to either shrink or grow the physical shape, right? So we've had those words like isometry, something is isometric. We learned the word rigid, that all of the transformations we've seen up to this point keep the size congruent, right? We just slid it around, we just flipped it, we just rotated it. Now we're actually gonna do something that changes the scale. So it's gonna get like bigger, smaller. Okay, I'll stop doing that because that's crazy. All right, so that's what we're looking at. The pre-image and the dilated image are no longer congruent, right? So we were writing about congruent before, so it's not congruent. This is just what we call similar. And in geometry, similar means the same shape, but not the same size. And so going a little bit more specific with that, it does mean that each of the angles kind of stays the same. So like when I take a triangle and I just make it larger, this angle is still the same opening. Like it looks smaller, but if I were to take this baby triangle and if I drew this to scale, then in theory, I should be able to take it and like drag it over here and it's the same angle still. Or like this one here is the same angle over here. This one at the top is the same angle here, right? It's fast sketch, but you get the idea. Unless I was in the way, you couldn't see that at all, right? But that angle fits there, that angle fits there, down here fits here. We're just growing the shape. All right, the main things that you need to know is what does that look like as a rule? So it's going to look like x comma y, but there's going to be just a value in front of it. Like, hey, did you times it by 3? Then we're going to times every dimension by 3. Or maybe I divided them by 3, and for division, we'll represent that as a fraction like 1/3, or it could even be an uglier fraction like 2/3. It could be a fraction like 3/2. So we're going to kind of talk about that here. Generally, what enlarges a shape would be things like 4x, 4y, where it's clearly and obvious that you're like multiplying by a whole number that is going to grow the shape. But it also could be any fraction that's improper. So like 6/5 x, 6/5 y. That would also be an example of enlargement. As long as you remember that a fraction is multiply the top, divide the bottom. If I'm overall multiplying more, then overall this shape has grown some. And then a reduction is going to be anything that's like an obvious fraction but not improper. So it could be like 1/2 x, 1/2 y, or just anything like 2/3 x, 2/3 y, where as long as overall there's more division happening compared to the multiplication that's happening. These things will cause that to happen. The math name for the grow is called enlargement, and the math name for shrinking the shape is referred to as a reduction. So just if you see those words and for any reason that's thrown you off, that's what that means. Okay, We don't really do a lot of examples because, to be honest with you, it's not that complicated. So basically, if I say, hey, we're going to dilate this by a scale factor of 2, I already know this is going to be an enlargement because we are growing the shape by multiplying it. And so wherever the original points are, so like if t is here at -1, -3, r is currently at 2, 3, and I is at 4, 1, then when I multiply that, you just times everything by 2. So it's like -2 comma -6 times 2 would be 4, 6 times 2 would be 8, 2. And then when I graph those points, -2, -1, 2, 3, 4, 5, 6, that's my t prime. 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. R prime, and I is now at 1, 2, 3, 4, 5, 6, 7, 8, 2. I prime. When we connect those, it's still the same general shape, it's just physically grown, right? So all the angles should look the same, just kind of doing that. If I give you the original and the new one, and I ask, hey, what is the scale factor? The first thing I do is I look at one of the points, I look where its regular point is, and I look where the prime point is. And I immediately am going to know whether this is something that I'm multiplying by or if I'm sort of dividing it and it needs to be a fraction. So if I notice that A is currently at 1, 4, and then I notice that A prime is currently at 2, 1, 2, 3, 4, 5, 6, 7, 8, yeah, sometimes have the ability to tell like, oh dude, it's just timesing by 2. Perfect, scale factor is 2, done, next question, okay? Sometimes it's going to actually be a fraction. So let's pretend for a second that this was like 1, 6, and I'm not gonna write this one because I actually don't know what that point would be, right? Just off the top of my head. But if I know I went from a 6 to an 8, I know it's some way I'm sort of dividing or attempting to divide that 8, 6 or that 6, 8. And I'm gonna check if it reduces. In this case, yes. So I'm either dealing with, the way I tell students is just divide them in your head, shrink it. You're either dealing with a 4, 3 or a 3, 4. Like it's one or the other because those are the numbers. And you ask yourself, is this growing? Is this an enlargement? Or is it a reduction? Is it shrinking? And to me, like because it's growing, between the only two options I'm staring at, it would have to be the multiply more. Or if I notice that these were flip-flopped and so it shrunk, then I'm going to choose the one that's dividing more. So that, again, the answer to this question was 2, but just that's kind of how we're going to think about it. The other thing, just because I don't know if there's an example of it, is just to point out, what do I do if the scale factor is a fraction? Like what if it's, let's say we take the point, the enlargement formula is this, and the original point is like -4, 8. I want to know, hey, where's the new one? Okay, so this is where we're just going to do fraction math, where you multiply the top, divide the bottom. -4 times 3 is -12, divided by 2 happens to be -6. Okay, 8 times 3 is 24, divided by this 2 is 12. And if it's not a nice number, it might reduce to a fraction and just kind of deal with it. Like that may be what the answer is. But again, if I didn't give you that and I gave you these points and I said, hey, what happened from here to here? In some way, you know you're going to need to like divide these because 8 times what makes 12? Not a nice number. So in some way, you're like, okay, either 12 divided by 8 or 8 divided by 12, in some way reduce this. These both divide by 4. That gives me 3 over 2 or 2 over 3, right? These are my choices, but because I can tell I got bigger, I'm going to pick the multiply answer. And again, because I have a lot of practice of this, I know to divide the second one over the first one, but just in general, even if you know that, you just want to kind of check yourself, that's sort of what I'm looking for. And if this were ever multiple choice, guaranteed they have both of those choices there, and knowing which way it's going, super important. Okay. The other thing that we kind of talk about in this day, so it has nothing to do with dilations, because really that's not that hard. Like the hardest thing is multiplying a fraction. So here, if it's still on page 41, you'll flip to it. We're just gonna have a quick comment on symmetry. And we're not gonna do anything where we're gonna ask you to like actually rotate stuff and do any of this symmetry. It's more just identifying from a vocabulary standpoint, like, hey, does this object have line symmetry? Does it have rotational symmetry? Does it have point symmetry? It's possible to have more than one of these. It's possible to have 0 of these. So we're gonna kind of just talk about it quickly. I think the easiest one that most people know about walking into this class would be what we call line symmetry. And it means, is there anywhere at all that I can draw a straight line? It could be vertical, horizontal, an angle, it doesn't matter, but a single straight line, and this object could fold perfectly in half. So like a heart definitely can be folded in half that direction. If you can't see it too well in the video, this is a hexagon. Hexagons have lots of places I could draw a line. I could draw it straight down the middle. I could draw it straight down the middle this way. I could even draw it straight, kind of at that diagonal would fold in half. This has a lot of choices for line symmetry. So as long as there is some place a straight line could fold this perfectly in half, we have line symmetry. Rotational is kind of what it sounds like. It's if I were to take this shape and at any point at all while rotating it, it lines up with itself. So if I take this and I start to turn it, turning, and it matches up again, and it matches up again. In fact, it's hard for me to tell even where I started because as I spin it, it all matches. But as we're turning it around, that is going to be called rotational symmetry. You'll notice here kind of on the answer key to this, because it's easier to sort of talk about, this one says order 5. That means how many stopping points along the way do I have rotational symmetry? So technically we know that we start with that one as kind of like 1, and then from there we have 2, 3, 4, and 5. So we are in order of 5. This one, there's 4 different places that I could stop this and it would look the same all the way around. So that would be in order 4. And it may not have to do with how many pokey points you have, but you kind of want to watch what's going on. A lot of times it does line up with that. Now, if something cannot turn at all, like it's just like a really, like, I don't know, something, there's no line symmetry. This is kind of up to the individual. It says an object has rotational symmetry if there's a center point around it can be turned. The order of the symmetry indicates the number of positions. Order 1 implies no rotational symmetry. So that's what I was saying. It kind of depends how a teacher might ask for this. In my mind, that has no rotational symmetry because there is no way to rotate it. But if I forced us to think about it, they all technically have order 1 because that means just don't move. And yes, I look like myself. But to me, that kind of falls under the like, no duh category of things. So normally we're going to call that it does not have rotational symmetry. It's just more if we're being super picky. If I turn 360 or don't move, then that's the only time. So we consider that no rotational symmetry. Okay. The last one, and it's not difficult, but it's the one that I understand why it almost feels the same as this for a second. It's called point symmetry. And point symmetry basically just says, hey, check 180. Is this shape identical when I turn it totally upside down? So not like a perfect 90, not partway in between, but just here I am, upside down, do I have this? And so you could argue that all of these would at least have order 2 rotational symmetry, because if I look like myself like now and I turn upside down and I look at myself, then that's definitely at least order 2. It's possible to have more than that. But, and here's like a good example to go back and look at. This one here had order 4 rotation. If I turn this totally upside down, that's still the same shape. So this would also have point symmetry, just like it also has line symmetry I could draw. Okay. However, and this is like a good example to see that, this does not have point symmetry. Although there are places I can draw straight lines, and it has line symmetry. Although I can spin this and it will match up at different points, so it has rotational symmetry. But if I turn this immediately upside down, then that point is down here. And so I don't even know if I can try to draw that. But it's like the star shape. Ooh, yeah, pretend I didn't draw that. But it's like the star shape. I'll just do this because now I can follow what I'm doing. It's like if I took this and I turned it totally upside down, exactly upside down, the point's straight down, like it doesn't match up. So just because it's rotational doesn't guarantee point, although I would say if it does have point, it also guarantees minimally in order to rotation, although potentially it has more, okay? And so down here, there's exactly one of these that I disagree with the answer. So if you want to kind of glance at that, but this flower does have line symmetry. There's some place I can put this rotational. Many places as I stop to turn this, I can match up. And point, if I look at sort of how this part of the flower doesn't have a little line in it, and the upside down is also that same type, so perfectly upside down works. So this is an example that has all three. The butterfly is only line symmetry, drawing it that direction. Spinning this doesn't work, upside down doesn't work. Playing cards, kind of watch, like for a second you might almost think line symmetry here, but because of where this 7 is compared to here, that is not part of the symmetry. So that's a no. If I turn it upside down, kind of notice where this one is floating a little higher up. So upside down, that would float down here. So that's a no. And so if it's not doing that, and there's no other place I could rotate this. So that's kind of a none of the above. If we were being picky, we could say it rotates but order 1 only, but that's what we define as it doesn't have rotational symmetry. 10 also doesn't have line, but this time, because of sort of the symmetry of where these are, like if I were to draw this, I don't know if the smartboard will let me do this, because it might count these all separate, but we're gonna try those things as well as like where the 2 10s are. If this is all joined together, so when I go to rotate it and turn it around, although it's slid a little bit, you'll notice all the little pieces still match up. So it does, while rotating upside down, work, and because it specifically works upside down, that is our definition of point, so both of those. This is the one that I disagreed with. There is no line symmetry, and they didn't write that anywhere. And it almost looks like line symmetry if I draw a line here, but you'll notice kind of how this spiral is, like, oh, this part of the spiral doesn't exist on this side. Because it might look like these 2 pieces could, but even that's a little bit off. But just as we're looking, I agree that it doesn't have line symmetry. Rotational, yes, because if I sort of highlight what this is doing, I can grab this, turn it, even though the smartboard might be off a little bit, you know, you can see that it does line up. So rotational, I agree with. However, I disagree with the answer key saying it has point symmetry, because point symmetry means perfectly upside down. And so that would be like this, perfectly upside down would be like there. And so that's why I don't agree with that. Okay, but again, it's not gonna be like a coordinate graph, and I'm gonna ask you to do some math with these. It's just recognizing and the vocabulary of what kind of symmetry something has. So the homework really is just going to be over the dilations, just to kind of practice doing the math, but other than that, just recognize your symmetry vocabulary. Okay, if this applies to this year's video, then your test is coming up Friday. Otherwise, like I said, the numbers and the stuff, they may not match up with the video that we were doing. So have a good one and good luck.